With bonding video 5, we're still looking at Lewis structures, but slightly differently. Not just drawing them, but after we draw them, making sure they connect with any experimental evidence about how the atoms are actually bonded. And you're definitely going to see this type of question. Draw a Lewis structure, but then here's some data about it. How does your Lewis structure support that data, or how does it disprove that data? And you've seen some questions like that before. Here's a conclusion. Is that conclusion correct or not? So the first thing we're looking at is called resonance. And it's actually a really simple topic, but it's something that I didn't really totally understand the purpose behind until recently. So the idea behind resonance is that you draw one structure and it works and we follow all the rules and we have a nice Lewis structure, but there's actually a different way that you could have drawn it that would actually be correct. So you could make something follow the octet rule one way, or you can make it follow the octet rule the other way, and then kind of wondering which one of those two things is the better way to do it. So that's what that paragraph talks about. And what we find from data is that it's not that one of them is correct and the other's wrong, or that both of them are right. It's really somewhere kind of an in-between possibility here. So ozone is the name for the chemical O3. So when an oxygen molecule bonds with another oxygen atom, and we saw that with the coordinate covalent bond on the last example, we form ozone. And the way you could draw this is you could draw this with an oxygen on the left, double bonded to your center oxygen, single bonded to the right, or you could draw it with the double bond on the right. And you may think, well, it's just the same molecule flipped. But if we had different isotopes of oxygen, we could prove that the double bond was between these two atoms, or the double bond was between these two atoms. But what we really see is that neither of those are true. Data shows us that even though the Lewis structure shows a double bond here and a single bond there, or a single bond with a double bond, there's two bonds there that are equal in energy and equal in bond strength. So this isn't totally right because these aren't equal in energy or strength or length, and that one's not right, so it has to be something in between. And this is drawn a variety of different ways, but this double arrow that you see right here and the double arrows that you're seeing in the example below are the way that we show that both of them are correct, and it's really something kind of in between. So if we wanted to draw this, there's definitely an oxygen in the middle with two dots. It's definitely connected to these other oxygens, and in every single picture these oxygens have at least 4 dots on them. But on one side it's got 6 dots and a single bond, the other side has just the 4 dots and a double bond. The data says that it's not a single and a double, but it's somewhere in between, so we could draw this, and I'm going to try to do this. I've failed a few times at this, but we can draw that as, okay, that's kind of a dotted line there, kind of a dotted line there, implying that it's almost as if we have a 1.5 bond here and a 1.5 bond there, or these electrons, that double electrons, are floating back and forth. So we never truly have a single bond on one side or a double bond on the other side. Since there's no reason why it would be more likely that the double bond would be on the left or the right, there's no reasons why the electrons would stay in one of those positions. So it's almost as if, and we would have some data that supported, and later we'll be able to describe it with molecular orbital theory, but it's almost as if there's a 1.5 bond and a 1.5 bond. So with the carbonate ion, we have a similar situation. We've got Lewis structure that can be correct with a double bond here, here, or here. So it's not that there's a double and two singles, a double and two singles, a double and two singles when we see the data. It's as if there is 3 bonds, all with equivalent length. So let me erase this one here, so I have a little more room. So that would be, if I had my carbon, and I'm just going to move my carbon atom a little bit. So my carbon bonded to oxygen, bonded to oxygen, bonded to oxygen, and I'm not going to put the dots on those you hopefully understand or get the idea that the dots are still there, but it's almost as if there's kind of a partial bond here in each of these situations. And the number of dots aren't showing that there's 4 more electrons there. They're just showing that it's not a single bond, but it's also not a double bond. In this, we would have some data to support the idea that it's almost as if it's a 1 1/3 bond. A little bit stronger and a little bit shorter than a single, but not as strong and short as a double bond. So the resonance structures, or the idea of resonance here, is that we have 2 alternative but equivalent Lewis structures. So each of these are different, but they're the exact same in terms of fulfilling the octet rule and in terms of the way the electrons are distributed. So the atoms are placed in the same location. So we can't switch the oxygen into the middle and switch the carbon out. That's not resonance. That's 2 different compounds. Our atoms are in the same place, but the electrons are placed or represented as being placed in different locations. So this is not something that we do just for fun to say, well, let's draw as many pictures as we can. This is something that we use to describe data that is there. If there's data, or if there's an explanation saying that this structure doesn't really have 2 equivalent, or doesn't have a double and a single bond, we need to be able to represent that graphically. So resonance is something we would see when there's 2 possibilities that are completely equivalent to one another. And to understand if these possibilities are equivalent, we use a concept called formal charge. The definition of formal charge, you can see, is the charge an atom in a molecule would have if all the atoms had the same electronegativity. But what that really means is, if we're looking at each atom, how many electrons are around it compared to how many it brought. Because when we have an atom, it has a certain number of protons, it brought a certain number of electrons, and if it has more electrons around it than that, then it has the extra negative charge and therefore is negatively charged. If it doesn't have as many electrons as it brought, it has more positive charge from the nucleus than electrons and would be negatively charged. So this is all based upon assumptions of bonding electrons being shared equally, not thinking about polarity, and thinking about as if everything had the same electronegativity. So it is a tool that we use to understand whether 2 Lewis structures, are equivalent and exhibit resonance, but it's not really a description of what's happening with the electrons. So if we want to know what the formal charge is, we look at the electrons on each atom. If there are dots, those dots belong only to the atom on which they are found. So like this oxygen, all 4 of those dots, we would say that oxygen has those 4 electrons to itself. This nitrogen has these 2 dots to itself. This nitrogen has these 6 dots to itself. But when it's bonding, we treat it as if those electrons are being shared totally equally. So here, I'll draw a line, we kind of split these. Of those 4 electrons, yes, oxygen and carbon both have access to them. Yes, they belong to both of them to complete the octet. But for the purpose of assigning formal charge, we say these 2 belong to oxygen and 2 belong to carbon. Or if we split a triple bond, 3 to this nitrogen, 3 to that carbon. We split a single bond, carbon gets 1, sulfur gets 1. That's what that means. And then once we add that up, we can assign a formal charge. We look at how many electrons the atom brought, or the number of electrons in the neutral atom, the valence electrons specifically, and compare it to the number of electrons on that atom. So we're going to go through the process and assign them to all of the different atoms in each of these Lewis structures, the CO2s and the thiocyanates, the SCNs. So as we look at CO2, the oxygen on the left has 1, 2, 3, 4 of its own electrons. We split the bond, so it's got 1, 2, 3, 4, and then 5, 6. So it has 6 electrons. That's how many we would assign to it. so I will assign it 6. We know from the periodic table that it brought 6. So we do 6 minus 6. The formal charge on that oxygen atom is 0. That is just a shorthand of telling us it has the number of electrons that it brought. So I'm just going to write that right there. It has a formal charge of 0. The oxygen on the right has 1, 2, 3, 4, 5, 6 electrons. It brought 6 electrons, has a formal charge of 0. The carbon in the middle has no dots, but it gets half of each bond. It has 1, 2, 3, 4. Carbon has 4 valence electrons, so it brought 4 valence electrons. It has 4 electrons assigned to it, so it has a formal charge of 0. All very boring in that case. They all have the number that they brought. Down here in this other version of CO2, this oxygen has 1, 2, 3, 4, 5, 6 dots that belong just to it, plus half of that, so it has 7 electrons. Well, here it still brought 6, but now it has 7, so the formal charge on that oxygen is -1. This one over here, it has just 1, 2 that belong to it, and then it gets half of these bonds, so it's got 1, 2, 3 from the bonds, plus 1, 2. It has 5 assigned to it. It brought 6. 6 minus 5 is +1. The carbon brought 4. It's got 1, 2, 3, 4. Brought 4 has 4, so its formal charge is 0. So we're going to talk about why we would do this. Then we'll do another example with the SCN ion. So the reason we do formal charge is to figure out, are these two equivalent to one another? Or is this truly two different structures that we would consider resonance? So it says the dominant Lewis structure, or the one that is most common, or to simplify it, the correct or best one, is the one where we have formal charges closest to 0. That means all of the atoms have, if they're 0, have the number of electrons that they brought. Or if they have a formal charge, we want it to be as small as possible, as close to the number that they brought as possible. If they're not all 0, negative charges should go on elements that are negative. So as we look at these two, the first Lewis structure of CO2 has formal charges of 0, 0, and 0. The oxygens and carbons all have the number of electrons that they brought. The second Lewis structure is -1, 0, +1. It adds up to 0, but this oxygen has more electrons than it brought. This has fewer than it brought. So this is less likely, and that's actually the correct structure for CO2. It won't exhibit resonance because this one is favored over the others. Now we'll do the same thing because this is something you definitely need to practice with SCN. Then we'll see some other examples here. So with SCN, and I'm reading right to left on this only because that's commonly how the formula is written, thiocyanates, SCN, a nitrogen brings 5 valence electrons. So if I do all of my nitrogens here, the number of valence electrons will be 5, and then I'm going to look at the number assigned to each electron, or each atom, excuse me. This nitrogen has 1, 2 of its own, 3, 4, 5. It has 5, it brought 5, that's 0. Nitrogen number 2 brought 5, it has 1, 2, 3, 4, 5, 6. So it brought 5, it has 6. Its formal charge is -1. Nitrogen here brought 5, has 1, 2, 3, 4, 5, 6, 7. Brought 5, has 7. Its formal charge is -2. Now, looking at the carbons. Carbon bring 4 valence electrons. Carbon brought 4, it has 1, 2, 3, 4. 0 is its formal charge. Brought 4 has 1, 2, 3, 4. 0 is its formal charge. Brought 4 has 4. 0 is its formal charge. So on all of these carbons, they all have the same formal charge of 0. The valence electrons in sulfur is 6. Sulfur in this one has 1, 2, 3, 4, 5, 6 of its own plus 1 from the bond, so it has 7. It brought 6, it has 7, a formal charge of -1. Here it brought 6, it has 1, 2, 3, 4, 5, 6. Brought 6 has 6, a formal charge of 0. The last one, it brought 6, has 1, 2, then half of each bond, 3, 4, 5. Brought 6 has 5, a formal charge of +1. So we want to figure out, are these all equivalent to each other? If not, which one is the best? Well, the bottom structure has a -2 and a +1. It adds up to the total charge, but we're not as close to 0 as possible. So that one's definitely not as likely as the other two. So here we have carbons with 0. That's good. We have something that's 0 and something that's -1, something that's 0, something that's -1. So they're very similar there. But when we look at the second rule, if we have to have a negative charge, it should be on the more electronegative atom. The more electronegative atom is nitrogen. So this is the structure that is most likely. These can be resonance structures. They are equivalent Lewis structures, identical placement of atoms, different placement of electrons. But if we looked at data, we would see that it's most likely that this has 2 double bonds because the formal charge indicates this is the most likely structure. So with formal charge, we need to remember they're not real charges. The sulfur atom isn't a -1 charge and the nitrogen isn't a -1. It's a way that we keep track of where the electrons are compared to where they should be. Electronegativity difference is how we figure out if it's polar or not. So these different numbers here are not necessarily telling us which end is positive or negative in a polar bond. And they're different than oxidation numbers. If we were assigning oxidation numbers in a compound to figure out what's oxidized and reduced. So it's important that you remember that it's just a tool we use, but it's not actually a representation of what's happening in the atom. So we're going to do 2 examples here at once. Some Lewis structures for the phosphate ion, look at formal charges and figure out which one is best, and then some things with formate. So phosphate, PO4, has 5 electrons from phosphorus. We've got 4 oxygens, each with 6. And because of, I forgot my plus sign there, because of the -3 charge, we have 3 extra electrons. So when we draw phosphate, it has 32 electrons. So drawing Lewis structures, they'll all have 32 electrons. So every Lewis structure that we draw, if they're going to be resonance structures, they have to have that 32 electrons. So we're going to put phosphorus in the middle. We're going to surround it with our oxygens. We're going to start with single bonds, and then we'll fill our outer ones with dots. So we're doing that. It's good to kind of count as you go, and when we do that, we've placed 8, 16, 24, 32. We placed all 32 electrons. All of the oxygens have 8 electrons. Phosphorus has 8. So that is a correct and complete Lewis structure. If we looked at the formal charges on this, oxygens brought 6, but has 1, 2, 3, 4, 5, 6, 7. So that has 1 more than it brought. This oxygen, just like the other, brought 6, has 7, -1, -1, and -1, because all of those have 1, 2, 3, 4, 5, 6 of the own, plus half of the bond. They have 7 electrons, but they only brought 6. Phosphorus, it has a complete octet. It does have access to all 8 electrons, but for the sake of formal charge, we just give it half of them. It has 1, 2, 3, 4. It has 4. It brought 5, so its formal charge is +1. So on this one, every single atom has a formal charge. We've got negatives, we've got positives, and we need to think, is it possible to make a structure that's better than this? And as we think about that, what's tricky is The Lewis structure that we drew seems right in every way. We have complete octets. We don't have anything weird going on with that. We've used all 32 electrons. But because phosphorus is in period 3, it can have 8 electrons or it can have more. So instead of drawing all of these as single bonds, and that one was kind of ugly, I can draw one of these, that's not much better, as double bonds. So I still have used 32. 8 plus 8 plus 8 plus 8 is 32. Oxygens all have 8. This time the phosphorus has more than 8. But the reason to do this is it tells us to draw more than one, but also to think, is there a better way to do this with formal charge? Well, this oxygen, just like the single bonded oxygens on the other ones, all three of those are bonded in the exact same way and have the same formal charge. But the oxygen on top has 1, 2, 3, 4, and then half of the bonds, 5, 6. It has 6 and it brought 6, so it has a formal charge of 0. The phosphorus in the middle has 1, 2, 3, now it has 4, 5. It has 5 and it brought 5. So now that formal charge is 0. So our charges here, our formal charges, have to add up to the charge of the ion. So this adds up to -1, this also adds up to -1, but here there's more things that have a formal charge of 0, so that's better. So we think, okay, we made one double bond, that makes it even better. Let's do 2 or 3 or 4, and we could do this lots of different ways. I'm going to go kind of all the way to the extreme here of making these all double bonds. So you could draw this with 2 double bonds, you could draw it with 3 double bonds, or you could go, like I said, all the way to the extreme and draw it with 4 double bonds. And when we do that, we've still used 32 electrons, 8, 8, 8, and 8. Oxygen still has 2, 4, 6, 8. And what's good about this one initially is oxygen has 1, 2, 3, 4, 5, 6. That's how many it brought. So that double bonded oxygen and that double bonded oxygen and that double bonded oxygen and that double bonded oxygen all have formal charges of 0. So you think that's great. Tons of things have 0. But our phosphorus here has 1, 2, 3, 4, 5, 6, 7, 8. But it only brought 5. It has a formal charge of -3. So all of these, this adds up to -3, this adds up to -3, this adds up to -3, because the charge on the ion is -3. Now we need to decide which is best. The dominant structure is the one that have charges closest to 0. These charges are plus and minus 1. These charges are 0 and -1. Here's a whole bunch of zeros, but we have a -3. We don't want -3s. That's way more electrons than it brought. If we compare these two, this one has charges on all 5, whereas here we have 2 things that are at 0, and we have 3 things that are at -1. And the negative charge is on an element that has a high electronegativity. So the best one right here would be 1 single bond and, or excuse me, 3 single bonds and 1 triple bond. That is the best structure for phosphate. So I just cleaned up all of those Lewis structures, so we have some space to do number 4. It asks us to do 2 resonance structures for the formate ion, which is H, which has 1 valence electron, C, which has 4, 2 oxygens, each have 6, plus 1 extra. So we're going to do 2 pictures with 18 electrons. We'll put the least electronegative element, that isn't hydrogen, in the middle, which is carbon. We'll connect that to oxygens, connect it to hydrogen, and then we'll fill the outside with electrons. When doing that, we've placed a total of 2, 4, 6, 8, 10, 12, 14, 16, 18. We've placed all 18 electrons. Hydrogen's happy, it's bonded. The oxygen has 8, the oxygen has 8, but carbon only has 2, 4, 6. And carbon is not an exception, it needs 8. So what we're going to do is we're going to move some electrons in. So some of these electrons, either here or here, are going to become a double bond. And because we could do it from here or we could do it from here, that's our clue that there'll be resonance. So one structure we could draw would look like that. Another structure we could draw would look like this. And it's not the prettiest thing, but you get the idea. We could double bond to one oxygen or we could double bond to the other. Both of them use 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. Both of them have full octets on both oxygens and on the carbon, and both of them are single bonded to the hydrogen. Those are equivalent resonance structures, and we could do the formal charge on those and prove that they're equal. And just really quick looking at that without doing it, there's a single bonded hydrogen. That's going to have the same formal charge in each case. The carbon has 1, 2, 3, 4 bonds, 1, 2, 3, 4 bonds, so it has 0 formal charge. I have a double bonded oxygen here, double bonded there, single bonded, single bonded. So those are really identical. It's just electrons in different places. So those are two Lewis structures. And I can't put the oxygen in the middle. I can't put the hydrogen in the middle. I can't make a double bond here. I can't make a triple bond here. That would give me too much around carbon. We're not trying every possible different combination. We want things that follow the rules, and that's all they need to do. So then we want to draw formic acid, and formic acid would be H, C, double bonded O, single bonded O, and then we have to put an H on it to make it an acid, and we know from the acid-base unit that the hydrogen in an acid most commonly bonds to oxygen. So then the question is, which of these will it bond to? Does it bond to this oxygen? Does it bond to this oxygen? And we could draw it both ways, and I'm actually going to do that. So I'm going to draw it there, and I'm going to draw it up here. So I'm going to put the H there, I'm going to put the H there, and then fill in my dots. And the way that I can jump straight to these structures is they're based on my structure from before. I may have used too many dots on that one. There we go. I think that's better. So we double check. This has used 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16, 18. Everything, the oxygen is 2, 4, 6, 8, carbon is 2, 4, 6, 8, oxygen is 2, 4, 6, 8. Same idea here. So all I did was used some of the electrons that used to be a lone pair on this oxygen or on this oxygen to bond to hydrogen. In both cases I have a hydrogen with just one electron, so it's got a formal charge on the hydrogen of 0. The carbon has 1, 2, 3, 4, it brought 4, formal charge of 0. Has 4, brought 4, formal charge of 0. This double bonded oxygen has 1, 2, 3, 4, 5, 6, and it brought 6, 0 formal charge. Over here, we've got an oxygen that has 1, 2, 3, 4, then it gets half of this, 0. And then my last hydrogen is a 0. But over on this other structure, my oxygen's got 1, 2, 3, 4, 5, 6, 7. So it has one more than it brought. This oxygen has 1, 2, 3, 4, 5. It has one fewer than it brought. And the hydrogens again is 0. So we've got two structures here. At this point, they are not resonance structures because they are not completely equivalent. This is more likely than that. So the acid doesn't form either way. Once the hydrogen's on there, there's no longer resonance. The hydrogen is on a single bonded oxygen, and we have a double bonded oxygen on the other side. when the hydrogen's off of there and we have the formate ion, we do have that back and forth, or that in between going on, but because of the way the electrons are shared here and formal charge, there's a more likely and a less likely structure. So that may take a little bit of practice, and that's why we did the example with CO2, with thiocyanate, with phosphate, and with the formic acid and formate ion. And if you need to look at those again, definitely do that. But this is something you'll have to do. Draw a Lewis structure, figure out if there's resonance, and use formal charge to decide if one is favored over another.